Yeah, so I'll just record this so everybody can see how I'm going to kind of navigate my way through this. I feel like it just needs a little bit of an explanation, maybe to understand how to pull the data for these assignments. Kind of just like the tolerancing one took a little bit. We had to go over a couple examples, maybe for you to know how to search out your tolerance stuff. And so let's do that here. So I have loaded, I think last week I loaded most of the resources you needed in the tolerance assignment itself. This week I loaded most of the stuff we need into this resources for week 11. I know I haven't used this in every week, but I did this week because I could just localize the resources we needed here and we kind of need it for every assignment. So then it wasn't buried in assignment. So if I click on this, let's kind of peruse through this. So yeah, and I've got a fair amount of stuff, but essentially what we're going to do here is like it comes out of the same book that the tolerance worksheet stuff came out of. It is just an AutoCAD textbook, Engineering Graphics Essentials is what it is. It's the one I have up here on my. I'm going to order a classroom set in the future, but I'm still working from scanned in handouts for this year. But eventually, I'm going to order a new set of this book. It's a really good book. I actually really do like it. It's got a lot of good information. Everything we've done has almost come out of that book. Similar, I mean, like very similar assignments. So you've actually been working out of this AutoCAD textbook and you didn't even know it for the most part. This is actually a chapter out of it. I think at the time of this print, if I open this up, it's this PDF that I have open here. It was chapter 5, Once Upon a Time. It's I don't know what chapter it's in the current book, but it's the same information still. They haven't really changed the information. And even the charting they're using here is just it's old, but it still is I mean it's still applicable to today. But what I want to do is just be familiar with this document. So, I mean, this is a 32-page document. It kind of is redundant from what you'll cover in your Chapter 11 theory study. So I'll come back to this because let me just peruse through the resources that I have, and then I'll come back and start using them. But this one is just it's got good information. It's probably as long as your Chapter 11 stuff is, but it's redundant information. So we're going to learn about fasteners, internal threads, external threads, the diameters, the major, minor diameters, some of the common sizing that's associated with these fasteners and how they're yeah. What else we got? I mean, I mean the list of terminology around a fastener is pretty extensive. We've got screw thread, external thread, internal thread, major diameter, minor diameter, pitch diameter, crest, root, side, depth of thread. So this gets, I mean, what I'm saying is there's a lot of nomenclature just understanding the particular parts of a thread, which seems overkill. It does, yes. There's only a few that we're going to pull out and need on our charts, like major diameters, minor diameters. The pitch is really important. Stuff that really shows up in the thread note or the call out that we might call out on a print is what I really want to focus on. And knowing that, yeah, it's a pretty deep study if I'm going to have to manufacture these threads, if I'm actually the manufacturer, I'm the machinist cutting threads. Maybe there's a lot more to the process of making a thread than I need to eat. It's not even all captured in the thread node necessarily, but it's captured on charts generally for sure. So anyway, big deep dive study of the individual components of just what seemed like a simple thread that we've probably taken for granted all of our life. And we can go back to taking for granted it later. Let's just kind of nerd out on it for a week. But so I don't know, they show some stuff here. I'm just going to peruse through this kind of quick. Some different types of threads. Yep, there's more than just your standard little triangular thread. Okay. We've got some schematic representation. That's a kind of a different way to display threads. That's a simplified version, schematic version there. Okay. You guys may have already taken a test on this. Maybe it's coming up this time around. I think maybe this time around. Internal, external threads here. You can see that there's hidden lines shown and visible lines shown. So we'll talk about that when we actually draw ours. It makes more sense to me once I start drawing them rather than just sit here and read through all this and try to understand it. Like it's just better if we kind of work through some of these details as we draw it. But yeah, there's a way we classify threads. Good. Okay. So keep going here. Shows maybe a brief little, oh, and then there's metric threads. So their thread notes are going to be different for a metric thread than they would be for a standard thread. It gets into some charting. Maybe it even gets into some details on how to draw, but I'm going to not use this resource as much as another one, but it's also captured in here. Okay, we've got clearances. We show that there's specific design and how things need to fit. All right. And then I think it gets down to the bottom is all these really the last 10 pages of this are actually the assignments that we're doing. I've just pulled them into like Word document charts to fill out rather than have to fill them out here. But essentially, we've just pulled the last 10 pages of this document and made them into worksheets. And so that's where the worksheets come from, is this particular that particular file. So that's just this one. It's like a chapter five. So anytime anything references back to chapter five, it's referencing back to that particular PDF that is chapter five of that version of that textbook. So along with that textbook came Appendix B. We used Appendix A last for tolerancing. It was Appendix A from that book. Appendix B is the one we need this. It's from the same book. And so I think I have it up as well. So let me look at my Appendix B. It's specific to threads and fasteners. Yes, I think Appendix A was the tolerancing appendix. This is the threads and fasteners appendix. So it's kind of like the other appendix that we dealt with for tolerancing. It's got a bunch of charts, 26-page document of a bunch of charts I'm going to have to reference back to. And I feel like they're just a little more complicated charts here. So this is unified national thread. That's what that would be considered a standard thread or like a USA thread, I guess. It's dimensioned in, and so we have like this first chart is just it shows some nominal sizes of fasteners. So the interesting thing is once fasteners are below a quarter of an inch, we don't call them like 3/16 of an inch or an eighth inch. It's not that they can't; those still can show up. It's just that our chart, particularly when things are smaller than a quarter inch, they start to actually get a number classification. That's additionally confusing on fasteners is that they're classified, yes, sometimes by their size that we might be like more used to seeing. And this is probably a major diameter that we're seeing here when we see this size. And if you guys have used fasteners, if it's a bolt, you realize that, a half-inch bolt it's not a half-inch wrench that I need to undo it, right? Because there's a size difference from the head to the actual kind of shaft of the bolt, right? So it gets confusing to know what size of what goes with what. And yeah, so we'll learn a little bit about that. The more of that story is the more you use that stuff, the more you start to memorize which tool goes with which size of bolt, and how to identify them. Anyway, really small ones on this chart are actually a numbered type classification, and there's different type of classifications beyond this. This is just a couple of this is just one little chart. Okay, so then the next page, I'm not going to go through these all in super detail, but here the next page goes right into a metric one. So metric and standard are a little bit mixed up in this Appendix B. It might be like a similar chart in standard and then a similar chart in metric. And that's what's going on here. There's kind of like this catch-all chart on the first page of unified national threads. And then there's this metric kind of catch-all little chart that has some information. Okay. And then let me see the next one. Then we go into specifically, it looks like bolts. And this chart is definitely made for you to figure out the sizes of it. You can kind of see that even the diagram is going to help us figure all these variables that they show on that. They have these charts that allow us to figure out what the size is based off our major diameter or our nominal size. So in order to draw this is why when you go into those, group one and group two worksheets, you may have to come into these and start like crunching some numbers to actually be able to draw these the correct size. So your head's the correct size. And the reason why it's so critical is it's all been engineered to hold the loads that it's supposed to hold, right? Like it's an engineered design is why it's so particular. Okay. And here's like my hex head socket cap screw maybe with a different spline type bit. Luckily we're not drawing that one. Like I say, they get more complicated if you're going to draw some of these different uh for different ways to fasten it with different tooling. I think we get to draw this one though. So there's some counter bore and some counter sink information. Okay. So this Appendix B, we're going to use a lot this week. So I'm just going to at least click through it. There's some counter sink. These are like flathead machine screws. I'm not sure what they call them a head cap screw. Okay, yeah. I've known them as flathead machine screws is what they were called. Okay, which is like a bolt. Like it's like a bolt that does this, the way it nestles in with whatever your design is is different than just a standard bolt. Okay, then we've got some older, I view these as kind of old-timey one. Yeah, here's a flathead machine screw with a slotted. What was the first one? Oh yeah, this is much more common these days, I think. They still make these. They definitely still manufacture these. Like I said, they're just hard to torque down with that just the amount of from the bit to the head, how they can torque down is maybe a little bit, unless you've got the right bit exactly sized right, which we never do. We never grab the right tool for the job generally. That's why our fastener heads get stripped and they get worn and wobbled and then you can't fit the bit in them anymore. Yeah, that happens a lot because we're using the wrong tool, wrong size. Okay, but there's a couple different ones. We got round head, still countersunk. What else we got? We got just a whole chart on washers, another part of my fastener family. Split washers. All right, stuff we're probably familiar with seeing. We just got to kind of we don't have to draw any washers, I don't think. So we might have to figure out some of the charts for them, but here's a metric fastener. So above was standard. Now here's metric bolts, or they call them hex cap screws, hex bolts. Yeah, just because the head is a hex shape, hexagon, 6 sides. Okay. Then we've got the nuts that goes with those. I haven't seen any nuts for the standard ones. I think this is the first nut, which has internal threads. And then what? Another one. These are also metric, but kind of the same style as the upper ones. Then we've got metric again for countersunk and counterbore. Metric machine flathead machine screws. Okay. Oh yeah, this is almost like the design that that screw is going to go into. Here's the details of potentially what the size of how to draw that. Here's maybe how to draw it so it fits in here. Like this is maybe what it's going into. All right. Here's just a chart on clearance holes if we're talking about some fit classes, and we might see some of this terminology show up in a worksheet here. Normal, close, and loose. All right. And metric clearance holes. Okay, so that was a standard clearance holes, metric clearance holes, and the appendix. And then after the appendix C here, which just references, I added a bunch of stuff that we need that is specific to some of ours. So I found that working with just Appendix B, there was some data that wasn't clear on what the dimensions should be to draw. And so like last year I added this and uh, and I think some of this charting will help us on on some of the specific ones that we draw. I think from group one specifically, there's 7 different ones. They're kind of an old-timey one. I couldn't feel like the dimensions for them were all found in that appendix. And the reason why is because the assignment sheet, the 7 that we want to draw in group one, are from your theory textbook. And the Appendix B is from that Engineering Graphics Essentials textbook. So there was a little bit of a disconnect in the reference data I had for the actual ones that we were drawing. So I've added these ones. I've got a counterbore size chart. I think there was only one little sheet in Appendix B about counterbore sizes. So I've added this additional one. I think it helped me capture some dimensions that I was missing. I also added this, oh, sorry, wherever I am, the Philister head cap screws. So this one is definitely, I mean, it has specific applications, but it's kind of a fancy little fastener that is kind of like a kind of like a socket head cap screw, but so it's like the marriage between a socket head cap screw and a round head. So it's got so it's just a weird, and I would say these are used, I don't know, less commonly now these days, but I mean, they still manufacture them. If you go into Ace Hardware or Home Depot or Lowe's and look through their bolt bins, which you should go do. I mean, what else could you do on a Friday night? But they just go like, take your knowledge to work and go dig through those bins, and you'll see, those bins, you can spend years in those bins looking for bolts and looking for the right one. And so then, yeah, I think we have to draw an oval one. So that's also kind of a different, it's like almost got the countersink style, but it's slightly dome capped. And so I just felt like there was like things missing to draw these. They're really kind of tricky to draw. So that's a reference for that particular one. Then there's just some. This isn't the only kind of like drawing. I pulled this out of chapter 11 for sure because it kind of helps us lay out how to draw that, how to get the size proportionally correct, I think. Whether I use this, there's more than one place this shows up, but it's definitely from your textbook, chapter 11. And then the last one I have is just this one, right? Oh yeah, this one. I added another chart for the hex cap one. This is a socket head hex cap screw kind of hex cap. I don't know. Yeah. So we might need this one. And then it got cotter pins too. Yes, we have to draw cotter pins. So I think we needed this chart. I could have zoomed that in a little bit better. It's pretty small. I can zoom in on my previewer here. On group two, we have to kind of draw we have to draw a fastener and then into what it fastens into. And so there are some specifics on how to draw that and how to get the relief right at the bottom. And so I think I've added this to kind of help us maybe with, you know, some simple numbers to crunch to try to get that proportionally looking correct. So I'm going to nerd out a little bit. I mean, we would call this a blind hole. This is a fastener going into a blind hole, which means it doesn't go all the way through something, which means I have to this has to be designed correctly. Okay. So, and then I think that one of the ones on group two is this, a set screw we have to draw. And it's like a dog head or like a square head. Oh, dog point. And so it is captured in here. So some of the last stuff in this PDF is for group two fasteners for sure. Okay, but there is a lot here, a lot in this, and I'm going to use the heck out of Appendix B. I mean, this first one you may not use too much. It's just a great like reference thing. You might do more work out of chapter 11, just doing the questions out of chapter 11. Then you actually use this mostly I'm just showing that this is where these questions came out of. Let's look through some more resources because there's more here. That's only these two. I don't remember what this is. Let me let me pull up my copy of it. It's the thread bolt with graphics, right? Yeah, yeah. So I think this does come out of, oh yeah, I think this is imagery that I've pulled out of and whether I have, maybe I think it came with, this is definitely out of your textbook. This is the same. This is engineering drawing and design reference material for sure. They are showing you some pencil-y tricks on how to draw that, which does come into play when I'm kind of hand drawing in CAD like we are. Like some of their tricks in how to draw these is helpful. So they actually, I think they even go through how to draw them in a detailed view potentially, which we are going to go the simplified view. But yeah, so they've got some explanations here. Whether I use this or not, that's probably not exactly. I think it's good reference information. Feel free to take it, keep it. Looks like we've got some Acme type square threads there. Oh yeah, some common angles at the bottom of your relief. Okay, so blind holes need a relief at the bottom. Hey, that's the one. I think this is the imagery I did pull out. That's in that one. That's in our Appendix B now. So I must have felt like that was kind of important for Fastener Group 2. Here again, it shows this kind of old-timey drawing, which I've kind of matched, like the question you had, Riley. This, yeah, they kind of show it this way in old time. I think it's just because they get the profiles better, and then they don't align with the axes, is what they're showing. Kind of a different take. Looking for clarity, I think, is there a reason why. But anyway, this is good information. This will work. Obviously, these aren't the dimensions we need, but some of this we can actually use to our advantage, especially when we draw that hex head. Some of their trickery here is helpful. I'll use the same trickery they do here, and I'll probably put mine at these 45-degree angles at the end just to terminate the. And then there's some set screw stuff, and we might talk about where some of the stuff gets used, but. Yeah, anyway, this is a pretty big document. I can't say I'm going to use the whole thing, but it does break down how to draw some of this like step by step pretty well. Meaning, yeah, I think the one that's handiest is going to be how to do the bolt head on the one fastener that we have. There's some of those terminology things for these threads: major, pitch, minor diameter, major, yeah, pitch, crest, depths of threads, angle of threads, crest, root. Dentistry terminology, it sounds like to me. But some of the stuff we really need to know. So let's get into what's the next sheet. Man, this is a long document. I forgot. Okay. Good information. Oh yeah, there's the key seat stuff. Hub, key seats and keyways. All right. Okay. We probably won't use all that. That's a pretty lengthy document, but that is good information. Kind of forgot that one. So I've posted that one here. Thread terms handout. Let me open up this one. This is another resource we have here. thread terms. It's this one. Maybe this one is just a one pager. Oh yeah, so I feel like this one did come out. That one that I almost stopped at and looked at for a minute. This is just something it looks like dates back to 2010. This maybe an instructor. It looks like it's kind of on our original type uh our template from our drawings early. It may be previously they used to draw this back in the day out to this level of detail, but which I would only value as good as is just getting us to nerd out over the terminology and what they actually apply to the fastener. I think we can get the feel for it though just by working through the worksheet. So that's at least just a quick down and dirty one sheet right to the some of the key terminology about a thread. Okay, so that's that one. Let me see what the so it's more of that's more resource than it is going to be useful on my assignment. Key seat dimensioning handout. Let me pull that one. Key seat dimensioning handout. 5-page document. This one we do need, I think, for worksheet set 2 for group 2. I believe I need to come over here and just verify based off the shaft and keyway size of how I would know how big of a key it should go in. I can't remember if we do more of this than just seems like we use this a few times. And I know we only have group 2 has a keyway or key hub, I think, and a key seat. So that may be where we use this resource because I think this is all just about, yeah, I do remember digging through this and I think we actually recreate this drawing. I do think we do. So that's where we actually pull this information is going to be from this charting. Okay. So we don't need that till the secondary assignment. That's good. Or the last assignment of the week. An American Fasteners data sheets. I think this is just kind of maybe a little bit more current, but not necessarily totally up to date. But I want to say I pulled this one maybe because I was looking for other data, but I think I probably just pulled it from their website. It's still 2017. Maybe I didn't pull this. Maybe this is one that's maybe this one has lived in. But it's similar. It's just according to this company's here, right? Like these people obviously um, will sell you fasteners like a McMaster car would, and so they have these things on stock on hand. So they just have we just have some sheets of theirs pulled in here. Similar, like you would see this even on McMaster car if we go to pull a bolt and a thread from their online website, which they just had a good online website for a long time. McMaster has to where it's easy to identify what I'm looking for, the way they've organized it, and we'll familiarize ourselves with that later this week for sure, like Thursday, Friday time. So, but I can't say I can't remember if I came back to this and used it for anything in specific. So I put it on the bottom of my resources. It's just some more data. I think the main stuff I need is probably from Appendix B. And then a few specific assignments, I probably need that key seat and key dimensioning. Uh, yeah, this one is probably good to know. You'll see it in Chapter 11 studies. Okay, so let's go to assignment and start putting this to work, though. Let's see what we do with this stuff. This is all great. What the heck do I do with it? Well, let's go back out here to my module and start our Fastener Thread Worksheet. So I'm going to open this one up. And like I said, it's just kind of a bunch of problems to kind of nothing that we're drawing. Just remember that for this worksheet threads one, it's just mostly like learning terminology. So I'm not drawing anything from this particular set. It's got the links for those for where the assignment came out of, plus the appendix. I think all of these are going to come out of this appendix B. So and then there's the worksheet to download. So I got mine open, I think, somewhere here. And I will now broadcast over. I told you I would, but I haven't. So now that I'll start doing something, I will throw my screen to you guys. And let's dive in here for a little bit, get started on this one, and then try to look at this one in group 1 stuff so we can actually have something to start drawing to. But I've got mine pulled up right here. This one, yeah, this is it. Should be just blank and not filled out. Of course, I have one that's filled out on my other screen. I'm lucky like that, but it's because I've done the assignment before. But it's been a while. I had to knock off the dust of my brain cells, remembering that this was, and it was super complicated before. It's just hard to know where to find stuff. I feel like it still kind of is, even just me going over that stuff. I'm like, hell, you can get lost in this pretty easy. So let's just try to keep it simple here. So this is the worksheet I need. It really does, at the top, it does point me to, hey, I've got that textbook stuff. It helps me figure out some of the terminology. I've got that Appendix B. And remember, your Chapter 11 stuff is kind of helpful. And then specifically, I think down here it even mentions, I thought it mentioned like Chapter 11, some pages, but definitely like I have up page 358 and 359. That's kind of where they start to talk about uh, some thread callouts. Yeah, I've got my Chapter 11 open right here, and I've looked through here. So I'm page 358, 359 are about in the middle of that chapter, but it's kind of where they break down the what we would call as the thread note details. And that's really what I want to kind of start with is how to identify what the numbers in a thread note are. And that's what this assignment's going to help with. So let me zip. And so there's a bunch to fill out. They're kind of organized like our tolerances were a little bit. Like this is problem A, D, and F. So I'm just going to fill these out in columns. Columns are the problems here. So this first set is external threads. The reason why they called them 5.1, 5.3 is because it was out of that chapter 5 from that other book. But it gives us some data to work with. So it's already telling us right here. Like, so I'll fill out like, I'll try to go through like at least the first ones of some of these because they're all just a little bit different. So let me at least work the first one with you guys of pretty much every group here. So they already give us some information to work with. It's got a major diameter of 1/4 inch, which is really common that our bolts and our fasteners are called out by their major diameter. And what that is, it would help me if I do have that. I probably already closed the one. Let me just bear with me for a minute because technically this does kind of help me. Major diameter. So if it's saying what the major diameter is, I look at this, that just means it's the very largest diameter from like point to point on the threads. We would call that our major diameter. And that's usually how, like in a lot of cases, that's the first number of the classification, or how I would identify any kind of fastener would be by its major diameter, not anything to do with the head of it or what kind of head or whatever it's going on. It's actually just the biggest diameter of the fastener. So that's our major diameter. So this is actually helpful for me to have up as I go through the worksheet. And in this particular case, it's given us the major diameter is 1/4 inch. It says that we're in a series, which is a fine series. So we'll look at this on our chart. It'll show us there's maybe 3 different categories. There's like a coarse, a fine, and maybe an extra fine on some fasteners. Not on all, but definitely fine and coarse on most like unified American made fasteners. And so we're definitely like a unified. I think they call it unified for standard fasteners. So this is 1/4 inch. This is our regular, like I feel like it's, USA America sizing here. 1/4 inch major diameter. We're in a fine series. And then the class of fit says it's external. That's what 2 means. And on page 358, it kind of goes through those numbers. We got the major diameter, and then this is a fine thread. And that last is the class of fit. Yeah. It's on page 358, they kind of have it as letter D. Class of fit is the amount of tolerance. The numeral 1 means a large tolerance. No, 2 is general purpose, moderate tolerance, and 3 is for applications requiring a close tolerance. So class of fit is definitely like how loose or how tight or loose the threads fit together from an external to an internal. I really feel like the way they engage each other can either be really super tight and for high critical applications can be like a class 2 is just kind of a moderate fit, like a general purpose. So. And then we have like really sloppy for anyway. But I would say a class 2 is a quite common bolt, maybe a common thread relationship. Not stuff you maybe know before, but now that's fine. Now that's not necessarily how it looks when I read it, when I read the thread notes. But and then what it wants me to do is go ahead and write the thread notes. So the first thing I'm really asking here is, well, given all this information, what does the thread note look like? And so this is where I definitely am appealing to page 358 in my textbook, which I don't have that up to show you, but because I don't think I have. I would require you guys to have your textbook to that to look, but because I'm trying to think. Oh, I think it is in chapter. Let me just look for a resource that I do have up on my computer. It might be in this in the AutoCAD textbook PDF because I told you I think it kind of mirrors what's in your textbook a little bit. Let me just look down here where it wants so that we know how to fill out. What I'm looking for is how to fill out what does the thread note look like? How do I write out what the thread note looks like? I think this particular thing might show us an example somewhere. Let's look. And I could be lying. Well, no, like the thread note. Unified thread. So I'm starting here on page 8. Unified thread note. Just want to see if it had a good example. It is talking about the things that would make up a thread note, which is like a 7-step process kind of. In your textbook, it's going A through H is how they classify this. I should have, now that I've done this, I should have an image of what this looks like. It's going to look like this though. What you're looking at right here is a thread note that I'm circling right here. It's got a major diameter, then it's got some weird number, then it's got like this UNC could be UNF. This thing can change. Then it's got a 2A and an RH as right hand. So this is what a thread note would look like. This is what would become on our. This is what we as designers and drafters would put on our drawings or the actual thread notes. So we just have to understand how to build them. I wish there was a little better explanation in this. Here's metric thread notes. They might look like this. Sometimes they look simplified from this too. So that's like I just want to see. I don't know. I need to upload chapter 11 to this so you guys can look at so I could bring it up on screen when I'm looking at my textbook. But it's definitely page 358, so I'll keep saying that. Page 358 is what I'm looking at. They break down this thread note as the first thing that's going to be in your thread note is going to be the major diameter. So I'm going to go back to my worksheet here somewhere, and I'm going to say first part of your thread note is major diameter, which was already given to me in the problem. So it's just 1/4 inch, and and they write them as a fraction, pretty common. So it's like the thread note starts with the major diameter. It's usually the major identifier, and then they put a hyphen here, and mine will probably do that unless I kind of backspace, but um, and you don't have to put a space between your hyphen. I'm just trying to make this clear, but it would be like major diameter, and then it would be hyphenated. And in your textbook, they say that's letter A, the major diameter of the thread in inches. That's in inches, followed by a dash. So, and I'll just read to you what's out of your textbook here. The major diameter is generally given as a fractional value. The fraction numbers can be stacked with a horizontal fraction bar or whatever. I'm not going to go too into that, but it definitely is generally written. Your major diameters are written as a fraction in a thread note. So there's 1/4 inch. Then the next part of your thread note is your textbook calls it letter B. B is the number of threads per inch. So we have to know how many threads per inch this would be. What determines that is whether it's kind of like a fine thread or a coarse thread. Fine threads or extra fine threads have a lot more threads per inch than coarse threads. That's why we call them coarse and fine, just how many threads per inch they have. So where we might find that or how we might figure that out is we should probably hopefully have a chart because what we have here is we've designated that we're looking for how many threads per inch does a fine thread have. And so where I'm going to show you where that is. Let's look in Appendix B now. So a little bit of jumping around. Here's Appendix B, the very first page. I don't even think I have to go beyond the very first page. I think I can look at this as a unified national thread. So we're standard threads. These are external threads. External threads. Our size is 1/4 inch right here. So I can kind of look across. This is our major diameter and kind of look across this row and see what other data it gives me about this. But what it gives me is like a basic major diameter. So that probably is the decimal equivalent of the fraction there, essentially. Yep. And then it breaks down these columns as coarse, fine, and extra fine. And the way I know that it's talking about coarse or fine or extra fine is we add this UNC, which is Unified National Coarse, is what that stands for. And then there's Unified National Fine and Unified National Extra Fine. And that's the biggest that's like the biggest little like abbreviation that I get when I look at a thread note that I know that it's a not only the fraction helps me understand that it's a like a standard uh or unified national thread, but also that UNF or UNC and a UNEF being kind of a rare bolt that I didn't use too much. I definitely used UNCs and UNFs a lot. But so a thread node just helps me quickly identify, oh, this is just a standard thread. It's not metric. So what I need to know is that mine is fine. So I know that mine is going to get this little UNF along with it. The thing is, what they put in the front of it is they put the threads per inch in front of it. And so what we need is we don't have that memorized probably. Some of them we start to memorize when we use them a lot, but otherwise we just don't, and we can look at a chart. So I'm saying if I have a 1/4 inch fastener and it's a unified national fine, it's going to have this many threads per inch. So this particular chart gives us how many threads per inch right there. It's going to be 28 threads per inch for a unified national fine. And so my thread note I fill out like that. So I'm back over here and I'm saying it's 1/4 inch. And did I say it's 23? What did I say? 28? 28? Yeah, 28. So it's 28 on my thread note. If I jump over here. And I'm going to put that number first. That is threads per inch, has 28 threads per inch. And then I say UNF because it's a unified national fine thread. And I think you can put a space between those two actually. If I was writing it in like a leader line, like pointing to it on my drawing, I probably wouldn't put a space between the numbers. I'd probably this would all be probably, I don't know, but there would probably be a space between here. I might not put a space between my dashes, or I might, depending how much room I have on my leader line. But this is definitely what's going to show up on my leader line. 1/4 inch, 28 threads per inch, UNF. And then there's another dash that shows up here. And sometimes some threads they'll only show that much. Like that might be enough detail, especially if all of your threads are just general purpose threads. They're always right hand. Sometimes you'll just see it a 1/4 28. UNF might be the call out, and they might even drop UNF and be like it's a 1/4 28 thread. And so these get really shorthand in some applications. But here we'll just go to the next step, which is in our book. It says they call that it's like step D because step B was my number 28, which is the number of threads per inch. Step C in our book is putting on the UNC or UNF, and so it's the what we call is the series of threads are classified by the number of threads per inch. So UNC means Unified National Course, UNF for Unified National Fine, UNEF for Unified National Extra Fine. So it breaks down that. They call it step C when they're writing it in our book. When they move to step D, which is where I'm at now, your book says this is the class of fit. It is the amount of tolerance, which I just already read out. The 2 is a general purpose, 1 means large or sloppy, and 3 means super fine or really close tolerance. So really common to just see a 2 here. That's what the number we were given as class of fit is 2. So 2 is the class of fit. We were given that information. So the only thing we've really had to pull out of the chart is 28 UNF actually. 2, and then it always is followed by, if you're going to do this, usually it's followed by an A or B. And so it's step E in your textbook. It says A means external threads, B means internal threads. So this is actually, I wouldn't know this, but it was given to us. This is external threads we're talking about. So it's actually an A that goes in here. And that's why sometimes these are dropped. So that is the correct thread node that I may, if I put, there's even more that it could capture here. That's like a pretty decent thread node. It's got the major diameter, threads per inch, whether it's fine or coarse or extra fine even, and then the class of fit, that it's a general purpose, and then it's external threads. So that captures a lot of good information. You'll see a lot of programs like Inventor may already have these built in to identify this kind of thread. And it would look like this in Inventor to be able to identify it. So what's that? Oh yeah, it's 2 was given. So that is this whole area is like class of fit. So it's this number 2. In your textbook, it's either going to be 2 or it's going to be 1. And and 2 means external threads, 1 means it's like a nut or internal threads. So you'll just see that dropped a lot. Like it'll be explicitly known, especially and think of it because if it was called out on a drawing, it might be pointing to an actual bolt, and you wouldn't have to necessarily put 2A or whatever, unless the class of fit was something other than just general purpose. Then the 2 is really required. But A is going to be understood as external threads, B is internal threads. So you sometimes see that dropped, and anyway, just be prepared that you might see these in simplified forms in your future. But they can't even get bigger than this. So I'll just stop for a minute and say, yeah, this is all I need to know is maybe these three main categories that I've done here. But if you look in your textbook, they really have E, F, G, and H. And well, E was actually the external or internal. Their step F, um, um, which is if it's left blank, which ours is left blank, you can actually put LH or an RH after this 2A. And that just is like it's really only required if you have a left hand thread because those are odd, which means they're lefty tighty and righty loosey, right? And so we say like standard threads are righty tighty. I spin them clockwise to engage the threads, like to start. And maybe you've heard that said righty tighty, lefty loosey. That's because our standard way of fastening stuff is with a right hand thread, right hand to tighten, left turn to loosen. And so we don't usually put that on threads because it's just understood. The only time I usually put what our step F is in our book is when I have a left hand thread because people need to know that that is odd. It's left hand. There are reasons for that. Sometimes they'll mix those right and lefts when they don't want things to be able to be put on incorrectly. And so it prevents maybe the wrong fastener from or the wrong from going on in a wrong application, getting things in the wrong place. So sometimes designers and engineers will use it strategically so that parts can't be incorporated in wrong. Uh, and anyway, and then it's used for other reasons too, but it's generally right hand threads are more common. So we just drop that and we leave ours blank. The other thing that could be in a thread note is this letter G, they call it, and it's identifies a thread with single lead. A single lead is a thread that engages one pitch when rotated 360 degrees. So it's like a real special type of designation that I would have in G. And then they even go on to step H in our book. This location is for internal thread depth or external thread length in inches. This space is left blank when the drawing clearly shows. So anyway, yeah, your thread notes can even get bigger than what we've got. This is just a nice, pretty much what I would call like our standard thread note has these three columns to fill out, and sometimes even the third one is dropped. Okay, but let's now that's one. There's our thread note. What we need to know now is the pitch, and that means a pitch is, if I go back to my little cheat sheet here, right here, I hope it shows, yes, pitch right here is point to point on a thread. So point to point. It's not explicitly given in a unified national course system. In metric system, it is specifically given what the pitch is. But in the thread note. In our thread note, it's not explicitly given, right? We have 28 threads per inch. So we can figure out what the pitch is with a little bit of math. We just do like 1 inch divided by 28. And that's going to be that's going to be like how big the pitch is, or from one peak to one peak of the thread. And really, I could measure the pitch as either the outermost one, along the major diameter from the peak to peak. That's usually the easiest to measure if I'm looking with my caliper, trying to identify what kind of bolt is. Because sometimes you think about the reason why I might need to know this stuff is if I'm looking to design a round fastener or if I'm redesigning something and I've got some equipment that I'm working with, maybe I need to identify what the fasteners are that are being used so I don't detail them out wrong. So I might have to grab a fastener, grab my calipers, and do some measurements on the fastener to determine what it is that I'm going to call out in my print, right? So that's a common thing that why I have to nerd out over this stuff and to be able to maybe identify fasteners off a table or something, right? So a pitch is one way to identify it. Like I could measure from point to point, or I could measure in the deep. It would be the same dimension if I went to the depth here, which they call what? The root. If I measured root to root, it's the same as point to point. So that's kind of the same dimension, and they're the pitch essentially. So how I determine on mine, where it's not explicitly giving in the thread note, I have the information to figure it out if I pull up my fastener here and I say, well, this 28 is how many threads per inch. And I think I have a little bit of oh, I just have I just have some data here. Oh yeah. So pitch, we need to know point to point on one thread. I don't give you the formula for it is, so I guess I make you understand. And if it helps you to write this out, it's going to be like 1 divided by 28. But I'm going to write it in decimal form. So I might just say that equals whatever that equals. I'm going to pull out my calculator. So let's do it. It's 1 divided by 28. 1 divided by 28. This is going to be the thread pitch. And maybe I'll write it to like 4 decimal places. So that's like 0.357 is what I get. 0.357. That's how much this little, because it's a really fine, it's a small bolt, quarter-inch bolt is, or a quarter-inch thread is quite small. A fine thread up top that is really, really a small space. This is just barely over a 32nd between thread to thread. So this is 0.03, what did I say this? 0.0357. Yeah, 0.0357 is the pitch of this. So that's just a nice to know. It might be a way that I could identify this thing if it was laying on a table, whether it was fine or coarse, if it measured that from pitch to pitch or root to root. So the minor diameter is a little bit trickier to find out. I do have this little thing comes from the Appendix B. The minor diameter is going to be the diameter minus this weird maybe what I'd call as a constant, the coefficient here. So it's going to be the diameter, which is the major diameter, minus 1.02 or 825 times the P pitch. So it's kind of a weird, so it's almost like a formula to figure out what the minor diameter is, which is, let's look at my thread note detail one more time. Let's see, this is probably called out. So the minor diameter is going to be from root to root. It's going to be how deep the threads were cut in this thing. So we got major diameter, minor diameter, and pitch are kind of the three things we've nerded out a little bit on this. And why this is critical to know also is that the way threads get cut is you'd have to start with something that's at least the major diameter in order to cut these threads, right? So I have to start like some of the nerding out of us is like, well, if you were going to make these threads, it's going to be a machining type process. It's going to make these threads. They're going to cut these threads they're going to start with a solid shaft, solid material that's at least as big as the major diameter so they can cut this. And then they have to know how deep to cut it. And they also have to know like the thread angle and all this and how to actually make it so it'll twist into itself and have a twist. But they really need to know how deep to cut this. They need to know how big to start with, a major diameter, and then how much material is going to be cut out to cut it down into the minor diameter. So these are numbers that somebody that's going to make this is going to need. And sometimes when I design parts, especially when I'm designing, like if I like this picture because this shows that maybe this fastener is going to have to thread into this. That means this is why it's so critical that when I'm designing stuff to accept a fastener, I have to understand that concept of the hole has to be designed so that it leaves enough material for those threads to be cut, right? If it has to be a threaded hole, that means I start with a very small hole, something in its maximum material condition, and then they can come in here with like a tap, and even you can do this from your home. You can buy a tap set and drill a hole with a drill, and then cut the threads in it yourself by hand. I mean, this is something that I sometimes have to do at home or clean up threads at home. So you have to sometimes know how put the maximum material condition in of that hole so that I can cut the threads out and actually have the engineered design intent for that fastener. Just a little side note that trips me out about this is the interesting thing is when you take any bolt threads and you thread it into like an internal thread like this, it's like the first three threads are almost taking like 75 or something percent of the load of that. And everything thereafter is just a fraction of the load. So it's so critical to have these things cut and fit right because they start, just within the first three or four threads of engagement is where most of the load is being held. So it's super critical. Super nerdy, but if you like building houses, this might not interest you as much. But if you like building machine parts, this is nerd central here. But anyway, and so many failures happen because these conditions aren't met or they've been compromised due to having experienced a load. Like if something is pulled on these threads and maybe it hasn't broken my bolt or whatever, but it's definitely like compromised the internal threads. Well, then I can't even reuse those sometimes, right? Like this stuff can be destroyed beyond reuse. It's why like in some critical applications, they'll be like, probably when you're bolting doors on an airplane and you're doing that inspection, you're probably supposed to replace the fasteners every time you like check. Yeah, and there's like standard operating procedures for like, I think of airplanes that once you've removed a door to check it or whatever, you probably have to put brand new fasteners back in because they will say that once these fasteners have been torqued down, they've been stretched, they've kind of been compromised, their duty cycle is done. They would probably take those out, throw them away, put in new fasteners. So sometimes when maintenance gets done, those corners get cut, and we reuse fasteners over and over again, retorque them, retorque them, retorque them. Eventually, you've actually like ruined the fastener's potential to do what it's designed to do. So anyway, yeah, yeah. There's another tangent for you. But what did we figure out? I think we just need to figure out a couple more things. Minor diameter is one of them. So let's go back to my worksheet. Minor diameter. Let's do this equation here. So it's just going to be, I'll just do it as I'll just start here on my calculator and just punch it in as it is. It says it's going to be my major diameter, which is going to be quarter inch. So I'm going to type that in as a decimal, 0.25. It's going to be minus, and I'll build myself some parentheses here because I need to know it's going to be minus this constant 1.0825 times the pitch. And so I have that pitch now as 0.0357. And then I'm going to end my parentheses here. And I think this is, and then if I hit enter, this should be what I get. Yeah, yeah. So this is the major diameter. This is the minor diameter. Major diameter minus this kind of weird little formula of this constant. Some engineer, I feel like some engineers figured out what that 1.0825 is what I should multiply the pitch by to get for most of my diameters. So I'm just going to write this as four decimal places. The minor diameter is 0.2114. Yeah. And that's the end of this one. It's actually 2114, right? Yeah. So they're kind of painful to go through, um, but that's what we're gonna do. I'll uh I'll move to the next one and then maybe we'll take a break here. Maybe I'll try to get through this first sheet and then I'll just first column A's in each one here just to see how they change up. This one would be a course thread I'd be looking for. So if I went over to that Appendix B sheet on for half inch, I'm going to be looking down this course column for it's going to be a half 13 UNF or UNC, sorry, UNC. And then I might have to take 1 divided by 13 to figure out its pitch and then do that little formula for the this is for B. I'm just talking through how I'd look for B uh on the same column I was working on. Yeah. But I'll move on to the next row here. Yeah, let me move on to the next row. Oh, D. Sorry, I'm saying B, but it's actually D. For whatever reason, this is D, and then F is extra fine. So look in the extra fine column for a 3/8. I know. Yeah, I think this just matches whatever was in that book. Why make it easy, right? Why not make it more complicated? Like, I think it's, I think it's just because the original assignment sheets, maybe they weren't even numbered on the, I don't know. I can't say I did that on purpose, but there's no reason other than I don't know why. But let me see this A. So yeah, I'll do A's. Yeah. It could just say problem one, problem two, problem. I don't know why I've lettered them like this. I think I was matching something that was already built and I didn't really think through it, but I think if you still go back to that chapter, I think maybe this is part of it. I don't know. I'd have to go look. And we'll just proceed on. So this should be kind of the same concept here. This is 7/16 fine 3. This means it's an internal thread. So this is actually a kind of a nut potentially, or just something that I might have to cut internal threads through a hole or something. But so it's still going to have a thread note detail because it's just going to have the 3 in the end. So this is going to be fairly similar to the other. Oh yeah, but it does have the tap drill size. Okay, good, good. So this is going to be, it still starts with the major diameter, I'm pretty sure. Yeah. So that thread node always starts with that major diameter. So that was given to us in fractional form, not that way. Let's do this way. 7/16, right? Yeah, yeah. 7/16 dash. And then I want the threads per inch of a fine 7/16 fastener. So hopefully that's on that chart. Pull up my chart here. 7/16 right there. It's a fine thread, which is the middle column. So this is 20 threads per inch. Yep. I'm going to put that one in. 20 threads per inch. Back to my worksheet here. 20. This is a fine thread again. So this is a UN. Sorry, UNF. Yeah, UNF. And then we just would have the thread class at the back end. This would just help somebody if they maybe couldn't see clearly what you're pointing out. But like I said, if you were actually pointing out a nut on a drawing, you might drop this, but otherwise it would have a three. And then it doesn't really say that it's anything. So you could put 3A. Oh, wait. Yeah, yeah. Is that right? Oh, yeah. B. Yeah. Oh, yeah. So they're saying that this is, they're saying it's three is for the close tolerance. So they've actually used a fastener here that I'm not used to using too much. Two was way more common as a general purpose tolerance. So three is that fine tolerance. B is the internal. Yes. So this is a 3B. Maybe B is a capital letter like this. So A is external. External threads. B, and this is an internal thread. Yeah, yeah. B is internal. Yes. Okay. So this is the correct thread note. Yes, I like this. So because it's an internal thread, this tap drill size goes into what I was just talking about. You have to have enough material to cut internal threads. So you can't cut them to the major diameter and then have any material left to cut. You got to cut them. You got to pretty much have the minor diameter in some ways here. So the tap drill size and or diameter is going to be on that same Appendix B chart here under 7/16 on my fine column here. I definitely get my threads per inch, but then I also get this tap drill diameter. So this is 25/64 is what I want here. And I'm going to talk about this in just a second. 25/64. So let me see. I'm going to put that in. That's what we want to know. Tap drill size 25/64. I'm going to write it down here, 25/64. And then the pitch of that, I can figure out the same way. It's going to be, and I'll write out what I did. It's 1 divided by 20 because there's 20 threads per inch. So that's 1 divided by 20 equals, that's just to help you remember. Um, that's what I want to come up with, right? So that's coming back to my calculator and saying 1 divided by 20 is how many, is what the pitch is. 0.05 is what I get here. 0.05 threads per inch. Yeah, I think that's good. Um, so what I'm kind of interested in is what this looks like compared to this. This should be a much smaller diameter than this because it's prepared like a tap drill size means that's that kind of that maximum material condition of a hole that will give me the material I need to like cut threads into. So what I want to show here is that you know this is the major diameter of even though this is an internal thread, I'm also kind of thinking about what's going into it. So it's definitely the major diameter of the external thread coming in, the largest diameter, or it's going to be the kind of the root of my internal diameter and how they meet together. And so it's going to be like the maximum diameter of both of those. If I'm thinking about this here. No, you don't have to there. What's gonna notate that is that UNC or UNF is gonna be my real and just the fractional form of that's gonna be really be my like visual indicator that I'm not in a metric fastener. And so yeah, that's a good question, but not needed for the units. Yeah. Um, anyway, what I want to say is, so what I'm comparing here on those dimensions that were just given to make sense out of them is that on my internal thread, we're saying that the essentially the major diameter is that 7/16. So I'm just going back and kind of working this problem to death to try to understand what this number is right here. But this is my major diameter. And so if I'm going to look at what decimally that looks like, it's 7 divided by 16. 7/16 is this decimal, 0.4375, kind of the major diameter. I know the question doesn't ask this, but I want to compare what the size is to that tap drill size, 25/64. So I'm going to remember this. This is 0.4375 is a major diameter. 25 divided by 64 is this size. So this is technically the size of hole that would be bored in something that would allow me to now cut threads into it to match a 7/16 diameter. So it's really critical for me if I'm actually performing this work that I don't start with a hole that's just a little bit under 7/16. So there is no guessing game here of like, well, I need to cut some threads in to accept This is an internal thread situation. So, but I've got a 7/16 bolt in my hand. I need to cut some threads for this to thread into. And so I'm not just going to be able to randomly pick something that's smaller than 7/16 to allow some threads to be cut. I'm going to specifically pick this really critical measurement of 25/64. I'm going to drill that through, and it's going to be just a nice straight drilled through hole with no threads or whatever. It's just like a drill hole. And that's how they cut threads. Is first they'll do a hole, like a pilot hole at 25/64 in diameter. Now they'll come back with this tap, this special tool made to cut threads, and they will actually like cut those threads so that it will accept a 7/16. So really the through hole is going to be 0.39, and my fastener is going to be 0.4375 minus 0.039. Yeah, sorry, I didn't do that quite right. I wanted to go 0.4375 minus 0.39. So really my hole is like that much undersized to be able to cut. I mean, this isn't what's asked there, and I might be confusing the heck out of some of you, but I just wanted to explain that like a tap drill size is just a through hole that's been drilled, and now it's ready. It's going to be the proper size to start cutting threads. That's what that's for. So if you're ever going to do your own out of your garage on a drill press or whatever, you kind of have to know this relationship. This is really critical, the way that an internal is going to fit an external thread. If it's confusing to you, okay, just like put it in your back burner of your mind and be like, let me just figure out what is needed on the chart and just move forward. So that's a fine place to be. I'm gonna do one more, and then we can take like a 5-minute break. So this is the last one on this page, another A column here. So it's just a little bit different, right? It gives me that this is a major diameter here of number 0. So what I'm going to do, that's kind of weird. So I'm going to go over that chart on Appendix B here. Yeah, this is like a numbered size, but our chart carries some of those. So this is like a number 0. That means it's right here. It's actually very small. It's like less than a 16th major diameter. 16th would be 0.0625. So this is a very small fastener. Like it's a 16th of an inch. I don't know. I think of like almost like your glasses type. Like a number 0 is very small. In fact, it's so small that we don't even have coarse threads in that diameter, like in this diameter of thread. We don't even have close threads, or sorry, coarse threads options. They're just a fine thread. There's only one type of threads I can buy in this particular size of fastener, and it's a fine thread. And it has 80 threads per inch. So it's pretty fine threads. Yeah, yeah, yeah. Yeah, it's very small. Yeah, totally. It's very small. So let's see. So the way we actually thread note this is the major diameter becomes the first note 0. So it's kind of weird. These ones can be like if you're not familiar with fasteners and you see these thread note callouts, they can confuse you for sure. Like which so I'm gonna pull up my this thing here. The thread notes start with 0. We drop the pound sign, we just say it's 0. If yours shows up blue, it's probably because I had some answers in here one time that I coded in blue, so it doesn't matter what color. But it's so mine just happens to be blue that's okay. So 0, if I see a number here and I know, and it's still going to say 80 exactly. It wants to know threads per inch. So that's 80. And then UNF because it's a Unified National Fine. I'm still going to know what's going to catch my eye if I see this note. And then there's not even anything else to add as far as like, so these numbered threads are kind of a little bit different. And what I'm saying is if you saw this on your print, this is all I'm going to write. I'm not even going to write 2A or 3B or anything. This is just going to be 0-80 UNF. When I see that, it might confuse me if I'm not used to reading fasteners, but because of the UNF, I'm going to know it's going to cue me in that this is a standard type of thread. It's not metric. And then when I see 0 out front, I'm going to be like, oh, it's one of those numbered type threads. It's a very small, less than a quarter inch somewhere in there. So it's a numbered type thread. Yeah. Why they didn't keep fractional ones, I actually don't know. This is definitely a numbering system that was created long ago and is still in application today. So it's not something that's been newly developed. It's old-timey stuff that we've adopted. But it does have a major diameter, and I do want to know that, and it's on that because 0 doesn't really tell me what the major diameter is, so I didn't mean to open but I'm going to. 0, I want to know that this is the basic major diameter. 0.06 is probably sufficient for my chart here. So And CAD's totally overtaken my computer now. But it's malfunctioning CAD at that. I'm going to close it. It's locked up my screen. CAD, what did you do? It's totally trying to open, but it's locked up. I don't want it. Probably because I'm casting. It kind of does. I'm going to stop my cast for just a minute.
Yeah, it likes to hide behind your other tab.
It does. And really, it's really ticking me off right now.
No.
Mine definitely doesn't get the same prompts yours does, but I even have a task. I have to crash it myself here, so just bear with me for a minute. I gotta get my task manager up. I gotta crash CAD itself because it's crashing mine. Where's my CAD? Right there. End task, please. There we go. Get rid of you. And you guys can't even get to your task manager. That's also kind of funny. But you can't even force a crash without just pushing online. So, or wipe it or pushing your power button. So uh I was wanting to type this in, which is 0.06 is the major diameter. And there's really no notes I need for this. So looks like these are the numbered ones. And then yeah, I'll take a break here and then maybe and because I'll still work through some of these. It's kind of a labor. I mean, it's just mostly a worksheet day as far as I'm concerned. Um, because we're going to get a little bit more particular on some of these other columns. So I just want, I definitely want to cover each one, but I will stop this recording and say I'll do a part B for sure.